Welcome to another topic of statics. I'm going to discuss with you force vectors in today's lecture. The objectives of today's discussion, we would be discussing a 3D vector and how we can represent it in a Cartesian coordinate system. Then we are going to look at how we can actually find the magnitude and coordinate angles of a 3D vector in Cartesian coordinate system. Then we are going to learn about how we can actually add vectors in three-dimensional space. We would be covering today's lecture with some reading quiz. There will be some applications. I'm going to talk about a unit vector, 3D vector terms, and how we can actually represent them and resolve them, how we can add vectors in 3D, and then there will be a concept quiz, there will be examples, and there will be an attention quiz similar to what we went through last time during the previous lecture. So the question here is the reading quiz. You can read it. Question number 1 is that in vector algebra, as we are going to use it, is based on what kind of a coordinate system. Again, you can look at all the choices: A, B, C, D, and E. In vector algebra, the right-handed rule would be used. Okay, then there's another reading quiz. The second one, the symbols alpha, beta, and gamma designate the what of a 3D Cartesian vector. Again, the symbols alpha, beta, gamma designate the blank of a 3D Cartesian vector. Think about it for a few seconds. Read the answers. A is unit vectors, B is coordinate direction angles, C is Greek societies, and D is X, Y, and Z components. Obviously, Greek societies, it's not designated the Greek societies of a 3D Cartesian vector, the Greek symbols, but that's not the answer. The symbols alpha, beta, and gamma designate the coordinate direction angles of a 3D Cartesian vector. So this is just to warm you up, to prepare you for what's coming. So let's take a look at some of the applications of three-dimensional force vectors. Well, many structures in the real world, we use 2D as a simplification of the real world problem. In reality, the world problems are 3D, and many structures, they involve the 3D dimensional space. When I use the word structure, it could really mean any type of a structure, from building to electric poles to machines to bridges to you name it, that's included. In this case, this is a power transmission pole. It's those older types still used in many places. They're cheap, they're easy to build, but they're not very convenient, especially during the storm. So the power pole, it has wires helping to keep it upright, and they are pretty much everywhere that you see nowadays, although we try to move to underground electric power transmission, all that. But as you can see here, there are two cables. They are holding this pole down at points D and C. Point A is connected to the pole itself, A and B, and the distances are given. This is an example of how we can represent forces in this cable using Cartesian vector form. There's another application. This is a radio tower. this is a radio tower. So if you know the forces in the three cables, how would you determine the resultant force acting at D? That is the top of the tower. It's actually right here, this point. This is the marking right next to it. So again, three-dimensional real problem with all the dimensions that are given and the height of the pole, and vectors could be shown as such: x, y, z. This is the x direction. This is the y direction. This is the z direction. Okay. So let's talk about Cartesian unit vectors and what is actually a unit vector. From physics, and calculus, you've been introduced to the unit vectors, but let me introduce them to you again, as this serves as a review. So if the magnitude of a vector A, show it as A in white here, if this is the magnitude, okay, of a vector A, okay, and that's shown in yellow here. So for a vector A with a magnitude of A circled in as shown here, a unit vector is defined as U sub A, simply A divided by its magnitude. So it's a vector divided by its magnitude. Now, what are some of the characteristics of a unit vector? Well, its magnitude is 1. It is dimensionless. It has no units. It points in the same direction as the original vector A. So the unit vector in the Cartesian axis system are I, J, and K. And again, last time we talked a little bit about this. They are unit vectors along the positive X, Y, and Z axis respectively. So it's important to realize I, X direction, J is the unit vector in the Y direction, and K is the unit vector in the Z direction. So consider a box with sides A sub X, A sub Y, and A sub Z meters long. Those are the length of this box. And we would like to represent a vector A as such. We define it as A sub xi plus A sub yj plus A sub zk in meter. Don't forget the units. And that would be the Cartesian vector representation. The projection of vector A in the xy plane is A prime, as shown down here. This is the projection. Okay. So the magnitude of A prime, what kind of a formula should we use to find the magnitude of A prime? We pretty much use the approach that we use in 2D vectors. We take the square root of some of the squares, as shown down here. A prime would be A sub x squared plus A sub y squared, and then we take the square root of that, or simply raise it to the power half. That would be the magnitude of A prime. So knowing the magnitude of the A prime, again, the magnitude of the position vector A can now be obtained as shown down here. Again, the square root of some of the squares, as you can see here. Again, if this is in the case we want to use a two-dimensional analysis to apply it in a three-dimensional vector. So that's how it really works. So let's talk about the direction of a Cartesian vector. How can we actually define a direction of a vector in a Cartesian coordinate system? Well, we use the angles alpha, beta, and theta. That's alpha, beta, gamma. That's how we can actually define it. Remember at the beginning I asked you about alpha, beta, gamma. That's really the purpose here. So these angles are measured between the vector in either in the x direction, or y direction, and z direction respectively as shown here. So the angle of vector A with the x-axis would be alpha, the angle of the angle that vector A makes with the y-axis would be beta, and the angle that vector A makes with z-axis would be gamma. So this could vary from somewhere between 0 to 180. And if we use the fundamental principles of trigonometry, we can simply calculate the cosine of alpha, cosine of beta, and cosine of gamma as shown here. One is a sub x divided by a, the other one is a sub y divided by a, and the other one is a sub z divided by a. And that's really coming from the right triangle and the relations that we can use there from trigonometry. It's really pretty straightforward. So these angles are not dependent, as you can see. So if we change, it is possible that we change the angle of gamma and beta in this case, keeping alpha a constant. We can also change the angle of beta and alpha, but they're not really independent. So the relationships between these angles, they must satisfy the following equation. If we take the summation of the square, cosine square of alpha, beta, and gamma, it should add up to be 1. So cosine alpha squared plus cosine beta squared plus cosine gamma squared should be 1. So please keep that in mind when you do your calculations. The results can be also derived from the definition of a coordinate direction angles and the unit vector. So as you can see here, we can have a sub x divided by a I plus a sub y divided by a j plus a sub z divided by a k, and as such, if we add them up, we get the unit vector u sub a. And we can write u sub a as cosine alpha I plus cosine beta j plus cosine gamma k. We want to make sure that we know how to apply these equations. Later on, I'm going to go over some examples and demonstrate how we can actually apply these rules to solve one of the problems in Cartesian coordinate system. So how do we add Cartesian vectors? We just take the summation of forces, and that would be obviously the summation of all the forces in the x direction, multiply that by the unit vector I, the summation is plus the summation of all the forces in the y direction, multiply that by its appropriate unit vector j, plus the summation of all forces in the z direction, multiplied by the appropriate unit vector k. So that would be really the how we can actually add vectors in a Cartesian coordinate systems in 3D. So for example, if a sub x I plus a sub y j plus a sub z k is shown as a, and b is also shown as b sub xi plus b sub yj plus b sub z k, then if you want to add a to b or b to a plus b would be, we simply add a sub x plus b sub x and a sub y plus b sub y and a sub z plus b sub z. And the ijk, the unit vectors, also help us. It's going to guide us which components should be added together. And if we want to simply subtract b from a, we follow the same type of procedure. Instead of addition, it would be a subtraction. Okay, so some of the important notes that we need to know. Sometimes 3D vectors, vector information is not given in a form that is easier to work with. For example, it would be given in, we know the magnitude and the coordinate direction angles, or we know the magnitude and projection angles. This is the way we can actually easier, more convenient to measure them, but may not be as convenient to solve them, having this information. So you should be able to use both of these types of information and pretty much change the representation of the vector into the Cartesian form, as shown here. For example, the force vector F is given here as 10I minus 20J plus 30K Newton. I'm going to solve some problems and we see how we can apply this. Here's an example. There are two forces, F1 and F2, are applied to a hook as shown. So this hook is attached to a wall or some other members, and there are two cables. The forces, internal forces, are F1 and F2. One is 500 pounds, the other one is 800 pounds. The direction is shown as such, the way it's shown here. The resultant force in Cartesian vector form is what we would like to determine. So let's try to digest the problem. Let's think about it critically for a moment. As you can see, the angles are given. Let's see if there are any angles missing. But before we do that, we need to pretty much use the tools that we have from geometry and trigonometry. We need to first write F1 and F2 in a Cartesian vector form, and then we need to add the two forces. Of course, we need to add that addition can be done by adding the x and y components of F1 and F2. So first, let's resolve for F1. So if you look at F1, in this case, f sub x is 0, and f sub y is 500, because this is applied in the y direction. So in order to calculate f sub y, using the similar triangles with a ratio of 3, 4, 5, we take 4/5 of that, and that would pretty much give us f sub y, which is 400 pounds. For f sub z, we take 3/5 of that, and that would provide us with f sub z as 300 pounds. So let's write F1 in Cartesian vector forms. Again, don't forget the units. 0I plus 400J plus 300K pound. In this class, it is very important to use the appropriate units, and you will lose points if you don't use the appropriate units, or if you do forget to put the units right next to the answer, or if you forget to carry them on. So that was F1. So now let's resolve for our force F2, and then we would add the components together to get F. So there are two directions, alpha and gamma is given here, and we would like to find the value of beta first. Beta could turn out to be 0, could be more than that. By inspection, we see beta should be greater than 0. So remember that if we add the square of the cosine for angles alpha, beta, and gamma, turn out to be 1. The summation of square of the cosine of alpha, beta, gamma is 1. So we now substitute that, and knowing alpha and gamma, but not knowing beta, we can simply solve for beta at 75.5 or 104.5. It depends on where we measure it from. From one side is 75.5, from the other side is 104.5. So the vector is pointing in the positive direction, so we take the beta as 75.5. After calculating the beta, now we are going to use the unit vector, u sub a, cosine of alpha I plus cosine of beta j plus cosine of gamma k, and we pretty much use the angles. Remember, the reason we do this is because in this case the triangle, the length of the triangle, the right triangle is not given, so we cannot use the similar triangles. Instead, we are using the angles itself and take the cosine of those angles. As a result, not knowing angle alpha, gamma, and the one that we just found beta, we can simply add them up, use the ij component, take the cosine of those angles, apply them, multiply them by the magnitude of F2, which is 800 pounds. We can simply get F sub 2, and now the problem is almost solved. R would be F1 plus F2, or R would be simply 713I plus 600J minus 308K pound. So we pretty much calculated the result. So we have the coordinate direction angles. We can find this is the first part that I should have shown you earlier. So let's take a look at a concept question. You can read it, take a few moments to read that particular problem and see if you can answer the questions that are provided here to you. So first one, if you know the answer to this one, that's great. If you don't know, let's go over them together. If you know only u sub a, you can determine the blank of a uniquely. Magnitude, angles, components, all of the above. Well, the correct answer is B, because if you want to determine the angles alpha, beta, and gamma of A uniquely, you need to know both the unit vector and the angles as we just demonstrated. The second part of this, for a force vector, the following parameters are randomly generated. Okay, so we have a force vector, the following parameters are randomly generated. Magnitude is 0.9 Newton, alpha, beta, and gamma is given. That is all should be alpha, not really alpha prime. So if anywhere you see alpha in this context, make sure you turn that into alpha unless it's absolutely given in the problem. There is an alpha prime. So 30 degrees, 70 degrees, 100 degrees. So what is wrong with the 3D vector? A, magnitude is too small. B, angles are too large. C, all three angles are arbitrarily picked. And the reason for that is that's the alpha prime in this case. So alpha prime is correct in this case. Again, these are picked at random, and that's what is really wrong with it. All three angles are arbitrarily picked. And you can test that by using the cosine formula, sum of each angle, square them, and see if you add them up, it's going to give you the results. Okay, so let's take a look at another problem, what I like to call a group problem solving. Okay, so let's take a look at that. So given the screw eye is subjected to two forces, okay, F1 and F2. Okay, the magnitude and the coordinate direction angles of the resultant forces is what we are what we try to determine. So we need to find the magnitude and the coordinate direction angles of the resultant forces. So what's the plan here? Okay, so the plan is we are going to use the geometry and trigonometry. We're going to resolve and write F1 and F2 in the Cartesian vector. Then we add them to get F sub r, and then we would determine the angles. That way we know the resultant force, both the magnitude and the direction. So first, let's resolve the force F1. Okay, as you can see, we are going to show you how we can use F prime, the projection of F, to be able to calculate that. So F sub 1z is 450 sine at 45 degrees. F prime should be 450 cosine of 45 degrees. F prime can be further resolved as F sub 1x and F sub, it could be resolved into F sub 1x and F sub 1y using the sine and cosine appropriately of the 30-degree angle. Now we can write the magnitude of F1z, F1x, and F1y. So F1x is 159, that's minus 159. I note that I'm carrying the sign, plus 276j, and that's F sub 1y. We turn out to be 275.6. We rounded up into 276 plus 318.2 Newton. We rounded that up to 318 k Newton. So that's F sub 1. Now let's resolve force F sub 2. First, we need to find the value of gamma, right? So knowing alpha and beta, we use the law of cosines, and we calculate the unknown, solve for the unknown, which is gamma. So gamma turned out to be 120 degrees. The force F2, and now we're going to represent that in Cartesian coordinate system using the cosines of the angles alpha, beta, theta. We simply know the magnitude of F sub 2. We multiply that by the appropriate cosines, and knowing alpha, beta, and gamma. So cosine 45 degree I, that would be alpha. Cosine 60, that's cosine of beta, and the cosine of gamma would be 120. Note that they're not squared anymore. That was just up here for this particular formula. For this formula, there is no squared involved. I'm usually pointing, this is the head of the arrow, pointing in which way. It doesn't always turn out to be pointing in the right direction, but I show the arrows as such, okay? All right, so then we pretty much take the cosines multiplied by 600, we get the magnitude of F2 as such. Okay, we round 420. We round up 424.3. Okay. So now F sub R, F1 is calculated, F2 is calculated, F sub R would be simply adding these. Note that I am using the plus and minus sign here. In this case, for example, 159.1 is negative, plus 424.3, that would be 265.2. Again, I'm adding these two, okay, both positive, that's 575.6, and I'm subtracting 300 from 318.2, that would be 18.2, that would be F sub R. Now let's find the magnitude and the direction of the resultant vector. Again, F sub R is the resultant vector. We take in order to calculate the magnitude of the resultant vector, I simply use the square root of sum of the squares. So I take the sum of the squares, F sub R, and this is the x component, y component, and z component. I square them as such, take the square root. This will be the magnitude of F sub R, the resultant force. Taking the inverse of the cosine of F sub Rx divided by F sub R, and that would be the angle alpha. Again, we are really following the formulas that we've already introduced to you. Nothing magic about these. We just need to know how to apply them. f sub r sub y. Remember, this is a vector, and it has the ijk component. So f sub rx is 265.2. F sub ry is 575.6, and f sub rz is 18.2. And as you can see, that's how it is calculated. Okay, so that pretty much brings me to the end of today's discussion. If you have any questions, please feel free to contact me. Let me cap this with an attention quiz. So let's take a few moments for you guys to read it and try to see if you can find the answer. So, what is not true about an unit vector u sub a? What is not true about unit vector u sub a? It is dimensionless. Its magnitude is 1. It always points to the direction of positive x-axis. It always points to the direction of vector a. Remember, we are looking for the one that is not true about this. The unit vector a is dimensionless, so that is correct. That's not the answer we're looking for in this case. Then its magnitude is 1. That is correct. It's a unit vector. It always points in the direction of the positive x-axis. That's kind of like iffy, right? U sub a. And it always points in the direction of vector a. This is correct. U sub a. But this is the problem that we have, and that will be the answer. Okay. Next, give you a few seconds to read this. If F is 10I plus 10J plus 10K Newton and G is, again, 20I, 20J, 20K Newton, then F plus G would be what? How many Newtons? I want you to simply, we add these, right? 10 plus 20, 30. So right away, it's either, the answer could be either B or D, right? And second one, 10J plus 20J, that's 30J. So right away, we eliminate. So we already eliminate this guy and this one. But now I eliminate this guy, right? And that will be the answer. The answer is D. Okay. Let learning